Hello and welcome back to Functional Analysis. I'm Fabian and together we are going to review a video from the bright side of mathematics on functional analysis. This video was the first video of the functional analysis playlist or series and deals with metric spaces. What we're going to do today is we're going to rewatch parts of this video, and I'm going to give you further details and informations and provide you with an additional example that may enhance your understanding of this very abstract topic. Let's start.
What you should know is that functional analysis is a really wide field. However, to get an idea of what it is about, you can just look at these two blocks. On the one side you have the linear algebra, and on the other side you have the real or complex analysis. In a rough sense, if you look at infinite dimensional spaces in the linear algebra sense, and if you want to apply some analysis for these spaces, then you are in the realm of functional analysis. Of course, there's much more to it, but if you have some knowledge in linear algebra and analysis, now you know what to expect. For example, here we consider spaces consisting of functions or of sequences, and of course also linear maps between such spaces. Because in this field we always combine algebraic structures with analytic properties, one often summarizes functional analysis just by saying it's the study of topological algebraic structures.
So, let me comment on this. We have these two sides of functional analysis, linear algebra and real and complex analysis. So linear algebra is the part that tells us about the study of vector spaces. So vector spaces are the central object here. And we do functional analysis. We are in particular interested in studying infinite dimensional vector spaces. But let us start with the basics again. So what was a vector space? A vector space, first of all, consists of a set. Let's call it V for vectors. And this set carries an additional structure, which is given by the addition. So we can take a sum of two vectors. And it also comes with another structure, which is given via the scalar multiplication. And normally we summarize this as a triple, so the space or the set together with two algebraic operations. What can we do now in the vector space? So given two vectors, let's say G and H from our vector space, and a scalar from our underlying field, so this field F could for example be the real numbers or the complex numbers, then we have now an algebraic structure that allows us to perform calculations like G plus H. This will give me a new vector. And we can also perform scaling. So we can also calculate something like alpha times G. Infinite dimensional vector spaces. Let me give you an example that we're going to study in today's session. So in the video, there was already the mentioning of function spaces. So let me give you an example of a nice function space. So we start out by saying that this space should consist of functions that we call f that have the following properties. So first of all, they are defined on the unit interval from 0 to 1, and they map to the reals. And we want these functions also to be continuous. Let us also give this new space a symbol. So the functions are continuous, and what one often finds is one uses a C to denote it's a space of continuous functions, and one also denotes the domain of definition here inside the brackets. So this space will now be our vector space V for the rest of the session. Now, for functions, you may recall that these functions naturally form a vector space. Let us maybe also quickly recall how the addition and the scaling of continuous functions works. So for g and h continuous functions, we now say, well, what is the sum of both of them? So this should again be a function that is defined on every point. And how do we define it? Well, it is the pointwise sum of the functions itself. So, and how is this defined? Of course, for every point in the domain of definition. Analogously, we define the scalar multiple or the scaling of a function in a pointwise fashion. So the scaling of g with a scalar alpha is defined as alpha times g at position x, again for every x in the domain of definition. So far for the linear algebra point of view. Now we want to do some analysis on the spaces. Why is this interesting? So at the heart of analysis and functional analysis, there is a process or a method that is called approximation. And approximation always means we start out with an object or a sequence of objects and want to improve certain properties, or we want to approximate something by a limit. And limits are something that we study all the time in real analysis. But in order to define a limit, so in order to define a notion that tells us that something is getting closer and closer and closer to something else, we need a further structure in our space. And this structure is motivated by the following need for a notion of distance. Yeah? So we need a notion of distance in our space in order to answer the following question. So given our two functions g and h, so how would we answer the question, how far apart are the functions g and h? Well, and the solution to this problem is not unique, but how we can do it is by making V, our vector space, a metric space. Because in metric spaces, we have a notion of distance, and, well, the distance of g and h will now tell us how far they are apart.
And that is the structure we call a metric space. A so-called metric space is not at all complicated. We start with a set X and we visualize that as a collection of points. For example, in the set X we have a lowercase point X, so just an element in our set, and another element we can call Y. If we just consider a set, we can't say anything about these points other than they are equal or not. So there are different points, but we don't know anything more than that.
So let's continue with our example. So we already have specified our set. Our set is the continuous functions on the unit interval. And now the video mentioned something that we can already do now. We can decide whether 2 points in our set, in our space, are equal. So how do we check whether 2 functions are equal? So just with the definitions here, we say two functions are equal. So g equals h in this vector space if and only if g of x equals h of x for all x in our unit interval. You see, up to now, we have not yet introduced further analytical structure to our space. This is everything that the space and the algebraic properties of the space bring to the table. And what we are now interested in is, well, measuring the distance between these 2 points.
Now, this is what we now want to change. We want to give the set X more structure. In this case, we want to know what the distance between 2 chosen points is. Now, if we want such a distance, then of course it should fulfill some reasonable properties. For example, if we choose 2 distinct points, then the distance should be always positive. Of course, the distance could also be 0, but only in the case when x and y are the same point.
So how could we now start to define a notion of distance in this high-dimensional vector space of functions? Let's start with an even more concrete example. Let's choose 2 functions, g of x, that we now choose to be x, so just a linear function, and the other function that we're going to consider h of x is the parabola x squared on the unit interval. Let's also make a plot of these functions. So they are both defined on the unit interval, and they also have the property that they map the unit interval to itself. So this is a fairly small sketch that we need here. So the linear function will look something like this, and the parabola will start also at 0 and be below, and then they meet again at 1. So how far apart are g and h now? So naively we would say, well, let us start out with a point x. Then we have a function value h of x here, and we have a function value g of x here. So the distance between both functions, well, it just could be this vertical distance here. So we would say, well, just calculate g of x minus h of x. So what else would we like to have for this distance? Note that g of x lies above h, so this value is larger than the value h of x, but it could as well be the other way around, and then we would get a negative distance, which would be something like not only a distance but also a direction, and we want this to be excluded from our definition of distance. So the distance should always be, just like the video said, something positive. Yeah, so this difference here would just be a real number, and to make it a positive number we use a property of the absolute value, which we know already from real analysis. Taking the absolute value is something like the natural distance of 2 numbers. Some concept that we already know. The distance of 2 numbers is the absolute value of their difference. We take the difference of 2 numbers and then add the absolute value to it, and then we get a positive real number. The real number being 0 if g of x equals h of x. Now the problem, if we would like to define a distance of functions in this way, would be that it heavily depends on the choice of x that we do. For example, if someone else came and said, well, let's use another point, x prime, to calculate the distance in the same way, then we would then say, all right, at x prime, we have a value h of x prime here, and we have also a value g of x prime here. Let's say the distance is again the vertical distance of the two functions here. We would get another distance. And you may already guess where I'm getting at. This is by no means unique. So we have, for every single point in our unit interval, we have a way to define a distance. So we could define also distance here, define a distance here, and so on. So we would never get something that is unique. And if we would say, well, let's just take it all together, we would not come up with a single number. So we want the distance to be a single real number that is greater or equal than 0. Think about this from a probabilistic type of view, from stochastics or from statistics. Let's say we are given two functions and we want to check their difference. What could we do? Well, we could just sample points on the interval and calculate the distance at this point. And we repeat this over and over again. What would we now do in order to aggregate all this information into a single number? We would take an average. And taking an average over an interval means to take an integral. And that's what we are going to do now to define our distance. We are going to say the distance between these functions could as well be just taking the integral from 0 to 1 of the absolute value of the function value difference at points x for all points x. So we are now taking any compromises. We are taking all possible differences and aggregating them into a single number by the means of an integral. Visually speaking, this also makes sense because what we are now calculating is the area between the two functions. So we are now calculating this yellow area between the two function graphs. And the way that we now defined our distance function tells us, well, we want to have a notion of distance that relates to the area that is between the two functions, the absolute value of the area. Keep in mind, we are taking the absolute values here in order to stay with our values above 0. We do not want any negative values for the distance. So, and with that, we could now just say that this here defines our distance function d. We are also giving it a subscript L1 because this is some kind of a Lebesgue type of distance of g and h.
In order to formalize that, we have to write down a map. This map is called a metric and it measures distances. And now it gets 2 points, so it lives on the Cartesian product of x with x. And it maps into the non-negative real numbers. So 0, infinity, where 0 is included. Now, such a map we call a metric if it fulfills 3 properties. And the first one we already know.
So before we get into the properties that this mapping is going to have, let us review what we now have as a definition for a metric. So we now have defined something that takes values between 0 and infinity. I just wrote it like this, r with the greater equal sign and 0, but this is just the same as saying it goes from 0 to infinity as in the video. So the metric now should be a map that is defined on the Cartesian product. So let me just copy down this definition in our case. So dL1, our L1 distance, is a map that is defined on our set. Recall what our set was. It was the vector space V that we defined to be the continuous functions on the unit interval. So I'm just copying the name of the space, so continuous function on the unit interval, times, so Cartesian product, continuous functions on the unit interval, and it maps to the interval 0 to infinity, positive real numbers. More concretely, this function takes a pair g, f, or gh. Let me just copy it and write it as above. It takes a pair gh and maps this pair to the following expression, the integral from 0 to 1 of the distance, the absolute value of the distance of g and h integrated over the x. This is now the definition of our L1 metric. So in the above example, with our function g and h here, we could just calculate now the distance in order to answer the question how far apart are g and h. Let's just do it. I copy this here. And for this example, let us calculate the distance. In this case, the L1 distance of g and h will be, well, per definition, the integral from 0 to 1 of the absolute values. So plugging in the definitions that we chose here, what we would need to calculate would be the integral from 0 to 1 of x minus x squared dx. So this is an easy exercise to solve this integral, and what you should get out as result would be 1 over 6. So the answer to the question, how far apart are g and h, how would you answer this question? Well, it depends on the metric that we choose, but we could say in the L1 metric, the distance between g and h would be 1 over 6. You see maybe where I'm already getting at. There are many different ways to define a metric. So to add this additional structure, this additional notion of distance to an existing vector space. I'm not going into details with that. We are just sticking with this single metric for the sake of this example. But keep in mind, there is not the one metric that you can choose. And this also shows you how rich function analysis can be. If we just stay with functional spaces, we have already a plenty of different metrics that we can choose. And of course, every metric has its own properties that will help us in some approximation problems. So there may be a metric that is better suited to solve the one problem than another one. But here we are just taking an academic example for you to get a feel for what we need to do and how we can define a first notion of distance on a space of functions.
If the distance between 2 points is exactly 0, then this is only if and only the case if x is equal to y. The second
Alright, Now let us talk about the axiomatic properties that a metric needs to have in order to call itself a metric. Because so far what we did here was I was just throwing out a definition, and I told you, well, this is something that we would say qualifies to be a suitable notion of distance. But in mathematics, we always want to have a precise definition for a term. And that's what we are going to do. Now we are going to step by step verify all the axiomatic properties that something or a mapping has to have in order to call itself a metric. I got ahead by just calling it the L1 metric, so spoilering you that this will be indeed a metric that fulfills all three properties. But let's take a look at them more closely now. So the first property that our metric needs to have is called the definiteness property. And the definiteness means, in our case, that the L1 distance of two functions g and f, or g and h, is 0. So the functions are not at all apart, they have distance 0 to each other, if and only if both functions are equal. So how would we now verify that the metric that I just showed you, that is here defined above, fulfills this property? Well, we would need to prove this equivalence here. And you know how to prove an equivalence. We need to prove two implications, and I'm going to show you the more simple one here. More concretely, we want to show that if g equals h, then this means that also the L1 distance, the L1 metric of g and h, equals 0. This is a fairly straightforward proof. We start out by recalling what does equality mean in our space. Well, equality means, well, two functions are equal if and only if they coincide on every point in their domain of definition. This means if g equals h, then we know that g of x equals h of x for all x in the interval 0, 1. So let me reformulate this, already having in mind that I want to write this, or want to recycle this information in the setting of our L1 metric. Well, if g of x equals h of x, this means that the absolute value of g of x, just need this one implication here, minus h of x equals 0 for all x in 0, 1. Alright, now we need to jump into the definition of our metric. How are we going to do this? Well, we need an integral here. And what we are going to integrate is this lower expression here. So because if the absolute value is 0, then I can write the following. I can then say, well, then the integral of g of x minus h of x dx over the interval 0 to 1. This is the same as integrating from 0 to 1, 0. Yeah, so this is the right hand side of this equality, dx. And of course, the integral of 0 is 0. But what did we write up here? Well, this is nothing else than the definition of our L1 metric. So going through this proof again, what we saw is I start out with an equality of functions. I reformulate this equality of functions in terms of my vector space. Then I integrate along it because my distance function, my metric, involves an integral, and I derive an expression that I can easily integrate. And then I come out at the other side of my implication, showing that the distance of these two functions is 0. In terms of the sketch, this would mean if two functions are equal, then, well, there is no area between the two function graphs. Something that is directly visible from a sketch. But keep in mind, this is just an example. There are fairly more abstract metrics and metric spaces where one cannot talk about anything that is easily visualized in a graph. But in this example, it works extremely well. So what you can do now is also try to prove the other direction of the implication, which is a little bit more involved. You will need some more information, some more knowledge on what you can do with continuous functions. Try it on your own. If you have any questions on it, let me know in the comments. Let me know how I can help. So far for the first property that we call definiteness. Definiteness, to summarize, tells us if two elements have distance 0, they need to be equal, and vice versa. Next property.
Property is also very descriptive. So if we look again at 2 points, x and y, and now we measure the distance from x to y. And of course, this should be the same as starting by y and going to x. So the distance from y to x should be the same as the distance from x to y. This means for the map, it is symmetric. It does not matter which is the first and which is the second element. You get the same result. And now the last property is where.
So symmetry means so the distance from one point to another is the same as from the other point to the first one. Let me just write it down here. So this means the L1 distance of two functions g and h is the same as the L1 distance between h and g. So symmetry means you can swap the entries or the arguments of your metric. Recall the metric was defined on a Cartesian product. That means you plug in one value and another value from the same set, and you can swap them and get the same result, which is intuitively clear if you want to have a meaningful notion of distance. Let us quickly show that this is also the case in our L1 metric. So this is basically just copying the definitions, because the definition of the L1 distance of g and h means we just integrate the absolute value of the difference of g and h over the interval. And now comes something very interesting. When we work in these complicated spaces, we recycle a lot of the knowledge that we already have in the finite dimensional setting and information that we know from real analysis, because something that we know is the argument of the absolute value. It does not care about the sign. Yeah, so we could just multiply everything that is inside our absolute value and don't change the value of the absolute value. Concretely speaking, this means that this integral, or more precisely the absolute value of g of x minus h of x, is the same as the absolute value of h of x minus g of x dx. Well, but going now back to the definition of the L1 distance of h and g, This just means that h and g have the same distance to each other. So what we have now shown with a very easy calculation that was hands-on, the metric that we just introduced to our space of continuous functions is also fulfills the symmetry property. So the property that we can swap the two arguments of our function. So we're already on the finishing line. Let's take a look at the last property.
Very important, it is called the triangle inequality. The name already tells you, now we consider 3 points instead of 2. So there's a point z. Now we have a distance from x to z and also distance from z to y. Now the triangle inequality tells you, if you go a detour, then your distance gets longer. In other words, if you add the gray lengths, then it gets longer than the blue line here. In a formal way, this means d of xy, the blue line, is less or equal than distance x to z plus distance z to y. Now with such...
So let us now also prove the last property, the triangle inequality. First of all, let me write down the definition in our precise setting. What we need is that the L1 distance of a function f and another function h is less or equal than the L1 distance of f and an additional function g plus the L1 distance of g and the function h. Yeah, so looking at the important parts here means, so we have the distance between f and h, and so this would be the direct distance, and it's always shorter than the detour through a third function g. Let us now prove that the L1 distance that we introduced fulfills this triangle inequality. I'm going to do this by adding the additional steps in between. The first thing, and this is very classic when we try to prove properties of a metric, is write down the definition that you have at hand. In our case, the definition of the L1 metric is just the integral from 0 to 1 of the absolute values of the differences of f of x and h of x dx. Next, there comes a trick that is very often used in, well, calculations of this type, is introduce a 0 that you can use for further calculations. The 0 that we are going to introduce here is just the difference of g of x and g of x. How are we going to do this? We are going to put this inside the absolute value by first subtracting g of x and adding g of x afterwards again to have a 0. And then we take the difference again with h, close our absolute value, terminate our integral, and we have still just reformulated the expression before. Now what we are going to use is, we are going to use a property of the absolute value, which is a very nice thing to do because the absolute value already fulfills a triangle inequality, and we are trying to prove a triangle inequality for yet a different metric here. And what we are going to do is, so we want to split this absolute value at this plus sign here. So this is very fast. So we just split the absolute value, leaving us with the absolute value of the difference of f of x and g of x. And then, well, the rest of the absolute value comes in here in a separate absolute value. So we used here the triangle inequality of the absolute value, and we also used another property, which shows you how rich this field of function analysis is, because we get to recycle a lot of information that we already learned in other courses. Namely, here what we used is also the monotonicity of the integral. Something that you may have learned in either your real or complex analysis course or in your course on measure theory. And we are now already almost done. The only thing for us to do is to use now an algebraic property of our integral. So once again, we recycle information. We build on the knowledge that we already have. And we are now splitting this integral into two integrals by using the linearity of the integral. So how do we do this? So we just split up the two integrals at the plus sign. So this is the first integral, then comes our plus sign, the one that I bordered here with the dots. And then comes the second part of the integral, difference of g of x, h of x, dx here. And now let's compare what we have reached. We have here a difference of f and g. Integrated, well, this is just the left metric here, the distance between f and g. And on the right hand side, we see that we have the corresponding expression for the difference between g and h. So this here is actually an equal sign per definizione. Let us zoom out and take a look at what we just proved. We started out with the L1 distance between two functions f and h. We fiddled in a function g, so to say the third corner of our triangle. Then we used the triangle inequality, but not of the metric that we are going to work with, but of the absolute value, which we already know fulfills this property. So we build on this knowledge about the absolute value. And after some further calculations, we arrive at the sum of the distances of f and g. So just looking at the expressions that have a green border shows us that the L1 distance between f and h is less or equal than the sum of the L1 distances of f and g and of g of h. To sum up, our L1 distance is indeed a metric according to the definitions of the video. With this, I think we can close this review. Thank you very much for watching. If you enjoyed this video, let me know via the like button. If you have any comments, questions, or remarks, let me know in the comment section. I'm already looking forward to it. Have a nice day and goodbye.